Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. This is the question show. Your questions, my answers. Now, as always, we've got little codes that we're putting up, which are your chance to vote for the question that you thought was the best. Now, last week, we had a tie for Shiny Galaxy asking which habitable star system excites me the most, and that was TRAPPIST-1, of course. And then also Dr. Brian Keating asked what were the odds the Event Horizon Telescope would show a movie of SgrA, and of course we know the answer. So congratulations to both Shiny Galaxy and Dr. Brian Keating for your excellent questions and my acceptable answers. Now, you can ask questions anywhere you like across my channel, across the YouTube comments. I will gather them up. I'll answer them here. You can also join the show live. We do this every Monday, 5 p.m. Pacific time. So come join live or watch the show afterwards. Either way, let's get into the questions. Cujo and Friends. Will James Webb look at SgrA? I got this question quite a bit. After we saw the incredible picture from the Event Horizon Telescope of SgrA, people were wondering if James Webb, the greatest telescope that humanity has ever created, will also be able to look at SgrA and do an even better job. And the answer is yes, and then no. So yes, James Webb is an absolutely phenomenal telescope capable of producing images that will blow everything else out of the water that's been sent to space so far. But it's just a single telescope. So the thing that's really important to understand about the Event Horizon Telescope, the one that took the picture of the SgrA black hole, is that it is a collection of telescopes spread out across the entire planet Earth. You had telescopes in Antarctica, telescope in Greenland, telescopes in South America, in North America, in Europe. And together, those telescopes, when they gathered their data, were essentially acting like a single telescope the size of planet Earth. And it's really hard. Like, James Webb is big. James Webb is 6.5 meters across, but it is not the size of planet Earth. That is a very big telescope. Now, the trick when you do interferometry, when you gather the light from many telescopes at the same time, is that it allows you to get the resolution of a telescope the size of the Earth. So literally, if we replaced the Earth with a giant telescope, you couldn't get better resolution than what was gathered by the Event Horizon Telescope. But it doesn't give you the brightness. It doesn't allow you to see really faint objects. So when you're going to do a big interferometer, you have to look at very, very bright objects. And in the radio spectrum, there's not much brighter than the supermassive black hole at the center of the Milky Way and the one that was around at the center of M87. So James Webb will absolutely be looking at the center of the galaxy at some point. And it's actually really well equipped to do that because it's an infrared telescope. And one of the big problems for the longest time is that astronomers were unable to look into the center of the Milky Way. They actually had a name for it. They called it the zone of avoidance. In other words, if anything you wanted to look at was located in the zone of avoidance, essentially obscured by the core of the Milky Way, there was too much gas and dust to be able to image it. But astronomers, when they launched space telescopes, were able to use infrared. And infrared, that wavelength, penetrates gas and dust quite nicely. And so very dusty objects like the core of the Milky Way or newly forming planetary systems, things like that, now suddenly you can see infrared through what would have been opaque in other wavelengths. And so some of our best understanding about the supermassive black hole at the heart of the Milky Way, SgrA, was taken with infrared telescopes. And sort of the greatest part of this is that we really learned, we confirmed, and this is Dr. Andrea Ghez, who won the Nobel Prize. She predicted and she observed using infrared telescopes the stars whipping around this invisible space at the middle of the Milky Way. And they were able to calculate the mass of this object. Whatever it is, it has to have 4.1 million times the mass of the sun. And so what James Webb will be able to do is do the same thing that these infrared telescopes did, observing the region around the supermassive black hole. But You'll get blobs of gas that maybe are in the area. You're going to see stars as they go by. You're going to get a much better measurement of the positions of these stars and use that to calculate whether Einstein was correct about gravity and things like that. But the resolution of the Event Horizon Telescope, a telescope as big as a planet, is just so much greater. And we talked about this, that the size of the object that it was observing was as if you put a donut on the moon and then you observed it from that distance. And so, yes, James Webb will absolutely be used in observing the core of the Milky Way, but no, it's not going to be able to do a better image than the Event Horizon Telescope. Hectic. Both images from the Event Horizon Telescope seem to show that both the black holes are oriented directly towards us. Now, isn't that a bit weird? Could you elaborate? Right. One of the big surprises from the team using the Event Horizon Telescope to image Sagittarius star was that it does appear that the black hole is roughly face on. Now, it's not face on like we're looking down one of the poles of the black hole as it's spinning, and if some powerful jet emanated from the black hole will be blasted directly at us. It appears off axis by about 30 degrees. And so that's like almost halfway, 45 degrees, right, would be oriented mix between us. And if it was 90 degrees, then we'd be seeing it completely edge on. So I wouldn't call that exactly facing us. It's kind of what you would expect as a random outcome from a random distribution. But the thing that was a real big surprise to the astronomers was that the orientation of the black hole doesn't line up with the orientation of the Milky Way. One of the big expectations is that the Milky Way is turning and has an axis of rotation, and the black hole, shouldn't it be rotating in the same way? And it's not. It's flipped over on its side. And that's weird. And that was a surprise. And it makes you wonder what kind of event happened in the history of that black hole that caused it to be turned over on its side. Probably some interaction with another black hole, or like a lot of material falling into it that was coming in from a funny angle. So we're going to need to do a lot more observations of the event horizons of other black holes to start getting a sense if there's any kind of lining up between the rotation of the galaxy and the rotation of the black hole. Jan Wares. Hey Fraser, I have a maybe somewhat morbid question I would be thrilled if you could answer in one of your next episodes. Is there any chance that biological debris reaches escape velocity during a big impact event like Chicxulub and orbits the Earth or crashes even onto the moon? Or to sum it in easier terms, are there dead dinosaurs drifting through space? Not a morbid question at all. It's an awesome question. And the answer is yes. When the Chicxulub event happened, when an asteroid 10 kilometers across smashed into the Yucatan Peninsula 65 million years ago, it hit the Earth so hard that it blew debris out into space, into orbit. And then that debris, because it was on a ballistic trajectory, re-entered the Earth's atmosphere, heated up, and then smashed into the ground. And so it actually heated up the entire atmosphere around the whole planet to the point that all of the forests around the world caught on fire together. There was tsunami radiating away that drowned whole continents. And it was a very bad day for planet Earth when that happened. So the question you're asking is, like, are there still dinosaurs in space? And it is possible. And the way we might know this is that when the Apollo astronauts went to the moon, they brought back a bunch of samples from the moon. And one of the most interesting samples contained a piece of the Earth. And so what they thought, what astronomers think had happened was at some point in the distant past, maybe the Chicxulub, probably not, a giant impactor hit the Earth, blew debris off the planet so far that some of it landed on the moon. And then other asteroids hit the moon, churned up this material, mixed it up with parts of the moon into a rock. And then it was probably dug down deep into the moon, and then another impactor brought it up to the surface, and an Apollo astronaut happened to pick it up and bring it back to Earth. And then when planetary scientists were studying this rock, they realized, based on the chemistry of the rock, that it had originally come from Earth. So if a rock from Earth made it all the way to the moon, then it is conceivable to think that chunks of dinosaurs were in some kind of orbit around the Earth. But probably not whole dinosaurs, parts of dinosaurs. Susie Turquoise Blue. How do stars get bigger than red dwarfs? When fusion finally kicks in, does that not blow the rest of the gas away? Thanks. So I see how you're going with this question. Like, you imagine, like, the minimum star to ignite fusion is a red dwarf star, and it's about 15% the mass of the sun. And so you can imagine you've got a certain amount of gas, it's forming into this star, and when it hits, gas is still streaming in, but now the star ignites, and now the star is pushing out with its stellar winds, and that is going to stop material from being able to fall into the star. And the answer is no. I mean, obviously we have stars that are more massive than the red dwarfs out there. But your thinking is right, and you just didn't get the right size star. And so the reason is because the time that it takes for the material to accumulate into the star is much shorter than the time it takes for the star to actually undergo stellar fusion in its core, be able to start blasting out radiation. Like, it takes a few 100,000 to a couple of million years for this process, for the star to shrink down, ignite, and then start to blast out that radiation. But for the most massive stars, it does appear that that's the case. If you've got a star with, say, 65 times the mass of the sun, then it will ignite fairly rapidly. Lots of gas is streaming in, it's collecting into the star, it ignites, and then the winds that are coming off the star are so powerful that no more material can fall down onto it. And this sets a limit for the most massive stars that we see out there in the universe. That it's kind of interesting that there is an upper limit, around 85, maybe 65 to 85 times the mass of the sun, maybe 100 times the mass of the sun, is the upper limit for the most massive star that we can find out there. One additional thing to think about is that astronomers think that the first stars in the universe, the ones that formed shortly after the Big Bang, they were made with only primordial hydrogen and helium, and that it's possible that they were actually able to get much bigger, hundreds of times more massive than the sun, thousands of times more, maybe tens of thousands of times more massive than the sun, and then they would have exploded as supernova very quickly. And it's just these later generations of stars that seem, with more metals in them, seem to have a limit to the amount of mass that they can do. So you're right, just the wrong size star. Bravo 01. Hey Fraser, just like Newton's laws work at lower speeds and then Einstein takes over with higher speeds, could there be laws of physics that we have yet uncovered that surpass Einstein? I'm not saying that either Newton or Einstein were wrong, but could there be a realm where we need something else beyond Newton and Einstein to work? And do you think we will discover it by the end of the century? There are absolutely laws of physics beyond what we understand with Newton and Einstein. And you could think of it like a ladder, that Newton was able to accurately describe the motions of the moon and things falling on Earth, gravity, to an incredible precision that nobody had ever understood before. But later on, as better observations were made, astronomers started to realize there were some minor problems with the predictions made by Newton. The best example of this is the orbit of Mercury around the sun. It wasn't taking exactly the right amount of time. It wasn't in the exact right position that it should. It was precessing around the sun. And at around that time, Einstein had made predictions about what could explain that there was frame dragging, that was sort of shifting space-time around the sun itself, and that Mercury was getting caught up in that, and that changed the position of where you would expect it to be. And once you calculated the orbit of Mercury using Einstein's math, now suddenly you could explain those anomalies that Newton's methods weren't able to do. So are there physics beyond that? There have to be, because there are too many issues that still can't be explained under our current understanding of physics. But any of these new theories, as they get developed, they have to be backwards compatible. So in other words, whatever this new theory is, it has to be able to match the predictions made by Newton, has to be able to match the predictions made by Einstein, but then it has to also be able to explain the anomalies that are currently not figured out, dark matter, dark energy, other anomalies. How can we make quantum mechanics and gravity go together? There are these various issues. And ideally, it makes additional predictions that can then be experimentally validated. And so it'll say something like, if you look at blue stars on the 3rd of every month, they will have this speed. And astronomers go out and they're like, we never thought to look for that. And they go looking like, what do you know? You're right. And that will be sort of the best follow-on. So the laws of physics, we always say as we understand them, because the real laws of physics are vastly beyond what we currently understand. And as we slowly make progress, we fill in little pieces. And we may never understand them all. Even if we come up with something beyond Einstein, there will be that nagging suspicion that there's something beyond that beyond, and it will go on forever. M. Shepard. If a small primordial black hole passed through the Earth, would it experience any drag or friction? No. Now, if a small primordial mass black hole, so imagine like some black hole formed at the beginning of the universe and still hasn't evaporated till now, or maybe aliens fire a black hole they from their particle accelerator at the Earth, it would pass through the Earth. It might accidentally bump into a couple of particles on its way through the entire Earth. But even that is unlikely. It's important to understand that when we think about matter, and it feels like a physical object, right? When you're sitting in a chair, the chair is pushing back against you, but matter is actually mostly empty space. And when you have a primordial black hole, it might still have an escape velocity that goes beyond the speed of light, but it's a very small object, and it will have a very small cross-section. And the event horizon is going to be as small as an atom. And so the chances of this black hole bumping into a particle and gobbling it up are incredibly low. So even if it does pass through a couple of particles as it moves through the Earth, it'll pass right out the other side. No one will even notice. There'll be no change, and it will move on. More questions in a second. But first, I'd like to thank our patrons: Brian Foster, Echo 12, Connor F., Matt Walter, Paul Thompson, Just Askin, and the rest of our 987 patrons for their generous support. Want our videos with no ads? Join our community at patreon.com/universetoday, and I'll also remove all the ads from the Universe Today website for you for life. Jeannie Young. Has a lot of water been found on the moon? Not a lot of water, but a surprising amount of water has been found on the moon. And the discovery of this water comes back to the Chandrayaan spacecraft from India. And this was like about a decade ago. They went into orbit around the moon, and they had the right instruments on board to be able to detect the presence of water on the moon. And they discovered that there were seemingly fairly large deposits of water around the moon's south pole. More recently, NASA's SOFIA telescope, which is the big telescope on the side of an airplane, imaged the moon in the infrared wavelength and was able to detect the presence of water mixed in with the regolith, the moon dirt, away from the poles. And so the thinking is that there are places at the south and north pole of the moon which are in eternal shadow, that you've got a crater, and as the moon turns, the sunlight tries to come in and it can never reach the bottom of the crater. And so that part of the moon is just never melts, never gets hit by sunlight. And so it's just there. And we don't even know where it came from. Maybe it came from comets. Maybe it was left over from the formation of the moon itself. But it's quite exciting. And it's, in fact, the place that most of the emphasis of lunar exploration is going right now. NASA is sending a spacecraft, going to be sending a rover and lander to the South Pole to try and investigate this water ice. The Chinese have a rover right now at the South Pole of the moon on the far side, examining the lunar regolith. They've pulled a sample back from the moon to try and see if there's water mixed in with the lunar regolith. And when the astronauts return in the next couple of years, they're going to be going to the South Pole and again, trying to continue on this search for water. Water on the moon is really exciting because it allows us, one, it just helps us understand how water got on the moon and maybe give us some answers about how water came to Earth. But also, it's a repository of resources that astronauts could use. You could take water, chip it out of these permanently shadowed craters, turn it into fuel or breathable air or water to drink. There's like a lot of water is the key to almost anything we're going to want to do out in space. And so it's quite exciting that water has been found, but it's not a lot. Like if you took a cubic meter of regolith, you would be able to get about a bottle of water, like a cup of water's worth out of the entire regolith. And that's a lot of dirt. It's far drier on the moon than it is on the driest desert on Earth. Harrison Stewart. Exactly how bad will the dust on Mars be? It depends on your definition of bad. So we did an interview about a week back about the regolith on the moon. And this stuff is bad. This stuff is very dangerous. It is broken up pieces of rock into like little glass shards. And they will get into everything. Wear down machinery, ruin clothing, get into your lungs, potentially cause various ailments. Mitigating this lunar regolith is going to be something that the explorers on the moon are going to be spending a lot of time thinking about and worrying about and dealing with. Now, on Mars, you've got weathering. So you've got wind that is blowing the Martian regolith around, and that will be rounding off the corners and making it less dangerous, less like little shards of glass and more like little pieces of sand. It's still going to get in everything, but it's not going to cause the same kind of damage. But I think it's still going to be about mitigating this stuff. The other issue is that the top layer of Mars has a kind of poisonous substance that is created through the interaction of the sun and the chemicals on the Mars called perchlorate. And it's dangerous. And you don't want to like take the Mars regolith, open it up inside, put water into it and breathe it or taste it or any of that. You're going to want to wash it and clean it and get that perchlorate out of it before you interact with it. Apart from that, I guess a sand dune falling on you. But no, it's not going to be trouble in the same way that the regolith on the moon is. Tom Watson. If a planet falls into a black hole and then the black hole radiates away through Hawking radiation, where does the planet go? Good question. This is the black hole information paradox. And this is an unanswered question right now. For the longest time, black holes, like what happens to a black hole, was not that much of a concern. I mean, obviously it's a concern. You will be dropping material into the black hole and the black hole will grab it and store it. And so this was fine. I mean, you've got a planet and now the planet has turned into black hole. But when Hawking devised this idea of Hawking radiation, he introduced this really weird paradox, because as a black hole is evaporating, and with Hawking radiation, and we've done whole videos about this and many people have done, so I'm not going to go too far into the details of it, but the particles that are coming off the black hole are coming from the event horizon, and they don't seem to be coming from the actual black hole itself. And so this violates one of the laws of physics about this idea of the conservation of information, that a planet went into the black hole and you can't just destroy the planet. You can't destroy all of the information that is associated with the planet, the location, the position, the spin of all of the particles. There's like dozens of factors that describe every particle inside any kind of one object. And it seems like a black hole, as the planet goes into the black hole, it wipes the information from the universe. And that seems to be just a paradox, a violation. And astronomers don't have a good answer for this yet. They are still trying to work. And there's been many ideas about it, like somehow as the black hole evaporates, it still releases the information that was encoded in the planet back out into the universe. There have been other ideas, and this is one of the big unsolved mysteries. If Hawking radiation is a thing, then this black hole information paradox is going to have to be sorted out, and right now we don't have a definitive answer for it. Gary Swift. Question. Larger telescopes generate larger data, which leads to an arms race between gathering data and storing and using that data. Are we approaching a point where the size of the data becomes prohibitive? Absolutely. We are at that point right now. With the Vera Rubin Observatory, and I forget the exact amount, but it's going to be dumping petabytes of data onto the internet. A ludicrous amount of data. far more data than you can easily download quickly to study the information. It's going to be taking this with what's the highest resolution astronomical camera that has ever been made. I forget the number, 100 gigapixels. And it's going to be shooting images every minute. And then it's going to be gathering up all of the entire sky every 3 days or so and just dumping all of that data in the highest possible resolution onto the internet. It's way too much data. But they are developing tools for the archive where all this data is going to go so that you can kind of pre-screen the data before you download it. And so you'll be able to do things like show me this one little spot of the sky, and then you're going to be able to download just the information that you need, because otherwise it's just going to be too big. But we have definitely pushed, if this is an arms race, we have definitely gone into the size of the data era being too large. And it actually offers up a lot of opportunities. If you're a database programmer and you understand how to work with gigantic databases, you can discover comets, asteroids, supernovae, all kinds of things. It's going to be all there in the data. And the limit is just going to be the capabilities of the programmers and the power of their machines to be able to work through this data. But that's fine. Better to have that data and figure out how to work with it later on. You can expect that over time, computers are going to get faster, the internet's going to get faster, our ability to manage this data is going to get easier and easier and easier, and it sure will be nice that we were gathering these ludicrously high resolution images of the entire sky since 2022, 2023. So it's funny, people always say like, oh, astronomers are hiding the data from us. Why won't they publish it online? It's online. All of it's online. The European Southern Observatory has an incredible amount of data that you can go through. NASA for Hubble, you can go through that. All of the rovers, all of the raw images that have been taken are there. If you pretty much name any mission that you can think of and then do raw data beside it, you will get the raw data. And then it's up to you to crunch it and answer any questions that you may have about the universe. Jason Cullen. Hey Fraser, what species do you think would eventually evolve millions of years from now to the same type of intelligence as us if humans disappeared tomorrow? Yeah, that's a good question. So who are your candidates, right? You've got the great apes, you've got chimpanzees and gorillas and so on. You've got birds, parrots, things like that. You've got dolphins, and I guess you've got octopuses. So if humans made themselves extinct, we're already ruining the environment of the chimpanzees and the other great apes. So I can imagine us taking them with us. Birds. My money's on the octopuses. They're living in the ocean. They can shift around their location, but they have a hard time using fire underwater. But I think they'll figure it out. Although, like parrots, birds are pretty smart. So I don't know. One of them. I like, it's like a Futurama episode, right? Where the different species rise up and then they blew it all up. And then like the cows, maybe? What is that? A slug, maybe? Yeah. My money's on the octopuses. Ravi, come up. Hey, Fraser, what do you think is the next big step in space propulsion? I'm excited about two technologies. So the first would be nuclear rockets. And we've talked about these in the past. You just have a fission reactor on board your spacecraft. You use the fission reactor to heat up some kind of propellant like a hydrogen gas. You blast it out the back of your rocket and you're able to achieve a higher velocity than if you used a chemical rocket. They've been demonstrated here on Earth. We understand how fission reactors work quite well. They should work well in space. And then we should be able to cut down the flight times from planet to planet. The risks of reactors, we think about the release of radiation here on Earth. It's, space is filled with radiation. So what's another fission reactor in space? And so I think that's the way. You build a reactor here on Earth, you launch it into space, you then fire it up, and then you use it as like a really fast way to get from planet to planet. The other technology that I really like is an ion engine. Now, of course, we've had ion engines for a while, but they don't produce very much thrust, but they're based on electricity. So you have solar panels. The solar panels gather electricity. They're able to use the ion engine as a propulsion system, and away you go. But if you can get more electricity, these things get pretty exciting. So one of the most exciting ideas that I saw, and this was fairly old, was a mission that would use a fission reactor on board and a very powerful ion engine. Still nowhere near as powerful as a chemical rocket, but still it would give you a lot of electricity, a lot of thrust. And the idea would be to make a spacecraft that was capable of, say, going and visiting all of Jupiter's moons. It would be able to fly to Jupiter. It could be able to go into orbit around Ganymede, examine Ganymede for a couple of years, and then leave orbit, fly over to Callisto, go in orbit around Callisto, and so on and so on. And so, once you've got a really powerful fission reactor producing a ton of electricity paired with a very powerful ion engine, that gives you a lot more ability, and it's a lot more fuel efficient. So a fission rocket would still be dependent on the amount of hydrogen fuel you'd be using as your propellant. But with an ion engine, you can fire these ions out the back much faster, and you can get by with a lot less fuel. So I'd say that is the technology that I'm most excited about in the near term. And then the other one, oh man, like a third one is laser sails. I love solar sails just in general, and I like the idea of laser sails as well. So those three would be the ones that I think are going to be the next big step. And it's going to be some combination of them for the future of space exploration. Christopher Ford, do you know if James Webb will be able to get a better read on the atmosphere in Proxima B and or monitor it for any kinds of technosignatures? Yes, this is the kind of thing that James Webb will be able to do, and do really well. So because James Webb is an infrared observatory, a very large mirror, it is going to be able to theoretically be able to observe the atmosphere of planets orbiting around red dwarf stars. And that's what Proxima Centauri is, and Proxima Centauri B. And it should be able to characterize, to understand the atmosphere of this planet and give us a sense of what it's made of. Now, we've talked many times in the past that even if you are able to sample the atmosphere of another planet and get a sense of like, oh, it's got lots of oxygen, or it has oxygen and water vapor and ozone and carbon dioxide and methane and all these things, there are natural processes that can produce these chemicals as well. So it's going to be really hard to make a slam dunk, oh, there's life on that planet. But the second part of your question was technosignatures. And again, the answer is probably yes. We actually did a story about this on Universe Today a couple of months ago, that James Webb should be capable of detecting some technosignatures, essentially the evidence of technological civilizations on nearby planets. Again, ones that it can study. So planets orbiting around red dwarf stars that are relatively close. And so what it's going to be looking for is chemical pollutants, things like chlorofluorocarbons in the atmosphere of the planet. And the cool thing about that is that if you detect chlorofluorocarbons in the atmosphere of a planet, then that is a 100% certain detection of intelligent life, because there's just no natural way that these very complex chemicals can form that we know of. And yeah, and this should be within the capability of James Webb. We're probably going to need to get some practice. They're probably going to need to find some planets and then come back around and do more observing time. But it is, according to this paper that I read, within the capabilities of James Webb, which is pretty exciting. Josh Kilburn, what country do you think is going to be the first to reach Mars? My hope is that it's going to be a collaboration. I mean, my money's on Elon Musk sending people to Mars first. He's going to, if they get Starship working, then they're going to send an uncrewed Starship to the planet. It's going to make fuel. If that works, they're probably going to send, I would guess, private astronauts, because NASA's probably not willing to take the risk yet. So, let's say they send an uncrewed spacecraft in 2028 and it starts building fuel. They could then follow on maybe 2030, 2032 with some astronauts. That's my guess, is who's going to first set foot on Mars is going to be private astronauts on a Starship. My preference would be a collaboration of many countries, kind of like the International Space Station, like all the Mars TV shows and movies that we've watched. You've got someone from Europe, and you've got someone from America, and someone from Canada, and someone from China, and they're all together. But if the US and I think like NASA and ESA, they're probably ready to do a mission to Mars in the mid 2030s to late 2030s. And that's sort of the same time frame that the Chinese are probably going to be in. The Chinese have actually started to release plans for what they're going to be doing with Mars. They're taking it very seriously. And so that's their eventual goal as well, is to send humans to Mars. So in my dream world, you've got this wonderful collaboration amongst many countries going to Mars together for all mankind. But my guess is practically it's going to be Muskatronauts who are going to do it first. All right, those are all the questions that we had this week. Thank you, everyone, for asking questions. Thanks to everyone who watched us live during the live stream. We do this every Monday at 5 p.m. Pacific time. You should see the listing for the next live stream. If you haven't already, subscribe to the channel, put in the bell, and you'll get a reminder when we go live every Monday at 5. All right, we'll see you next week. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber, Nancy Graziano, and Anton Poznikov.